All right, so I made a goof and I recorded this whole video, filled it out, and realized I didn't have my microphone on. So here I am re-recording. If you are sticking with me, awesome. Please know that this time the notes are already filled out because I didn't go back and erase them. But that actually means probably a shorter video for you if you need the help. Again, like the slides say, if you do not need to watch this video, by all means skip it. You will not be penalized in any way for already knowing what's going on and not feeling like you need this video. All right, so let's jump in. We're going to talk about rigid and non-rigid transformations. That just means, think about rigid being the shape of the graph isn't moving. You're just literally picking it up and either moving it left, right, up, down, or flipping it, but not actually making the shape change at all. But non-rigid would be like when you make it skinnier or when you make it wider. We're going to call those stretch and compress or stretch and shrink. Those are non-rigid. Hopefully you remember these. If the plus is on the outside, like in the first one here, it means to go up. Whereas if it's minus, it means to go down. If it's on the inside and it's minus, it's right. If it's on the inside and it's plus, then it's left. Hopefully that's all review for you. Negative on the outside is across the x-axis, whereas a negative x on the inside is across the y-axis. Non-rigid, like I said before, are your stretch and your shrink. If the number is large, it stretches, so it becomes skinny. If the number is a fraction that is less than 1, then it is a shrink. Notice we're not talking about any type of negatives. We're only talking about positives. The reason we don't have to talk about negatives is the negative, it would still be the same shrink or stretch as a positive. It would just flip. That would be the only difference there. All right, so here are some examples. If we think about the parent graphs, which I did not draw originally, maybe I will this time. So the parent graph, the absolute value of x just starts at 0, 0, and it's a V shape. Notice the plus 2 on the outside just means up 2, whereas if I had a minus, it means to go down. So the parent graph here is a parabola. So notice same shape, just literally moving up or down. Here, the parent graph looks something like this. The minus is on the inside, so minus 2 means to move the entire graph right 2. Your parent graph for square root function looks something like that. So for this particular one, it means to go left 3, so it's like picking it up and moving it left 3. Okay, what if I need to work backwards and find the equation? So take that off the screen for a second. If I look at the vertex and I notice that the vertex is 1, negative 2, that means from 0, 0, because remember your parent graph starts at 0. We went right 1 and down 2. So it's absolute value, so we rewrite that to go right 1 and down 2. For g of x, this one went left 2 and up 3. The only difference is that it is a reflection, so it is going down instead of pointing up. That means that we put a negative out front. What do reflections look like? So all the purple is just square root of x. A reflection across the x would mean that it would go this way. But this particular graph also goes up 2, so after the reflection, I moved it up 2. The next one is a reflection across the y-axis, so it's reflecting across the y-axis instead of the x. It could be left 2 and then reflect, or reflect and move left 2. Whichever way, it would still work. Order does not matter as far as which order when there's multiple ones. Okay, what about some stretches and compresses here? All right, so the purple graph is just your regular y equals x squared. What I did for the orange one here that was already graphed, think about a table. If I plug in 0 there, I get 0. If I plug in -1, I get a half. 1, I get a half. Plug in -2 and 2, and I get the numbers 1. Which means that, oh no I don't, I get 2. So 2 squared is 4, half of 4 is 2. And that's how I got my orange one. So notice that it is wider. Anytime it's a fraction, it will be wider. What about if the number is on the inside? So for the orange one here, f of 2x, where there was an x, I replaced it with 2x and then squared the entire thing. So I got 4x squared. Did the same thing for the blue one, so I got 1/4 x squared. To graph without a calculator, I kind of did the same thing here. I used these numbers to get, let's see, 2 squared is 4 times 4 is 16. 1 squared is 1 times 4 is 4. This is still 0. And then it's a parabola, so the other side has to look the same. The blue one, I used some different values. 0, 0 was still 1. If I plugged in 1, I got a 4th. Excuse me. And I didn't like that, so I tried plugging in 2. So 2 squared is 4, and a 4th of 2, or sorry, a 4th of 4 is 1. 3 squared gave me 9. 9/4 is not pretty. I don't want to graph that. So I'm going to put in 4. 4 squared is 16. A 4th of 16 is 4. And then I plotted those points and graphed. Notice the stretch, the normal one, and the shrink. And then of course we can combine all of those. So if I want to combine a step at a time, number 1 shows what a left translation would be, just moving it left. Vertical stretch just means the number out front. So notice that I put a 2 out front. And then down 3 would be -3 at the end. And last one, what if I reflect about the x-axis? The negative is out front. If anyone were to miss, I would guess that they forget to keep the negative out front here and accidentally put it on the inside. But since it is a reflection across the x-axis, it needs to be out front. And then showing that it went right 3 and down 2. All right, so that concludes 1.6 notes. If you stayed with me this whole time, thank you. Finish up your slides and your target, and you will be finished.